It is it's a terrifying moment. You're standing in the middle of a plant room. Maybe you're an engineer or a technician running a water treatment site right here in South Africa.
Oh, the silence is deafening when things go wrong.
Exactly.
Yeah,
Everything is humming along, the pumps are vibrating, the water's flowing, and then suddenly the process just stops.
yeah.
Or worse, the control panel lights up like a Christmas tree and the alarm starts screaming because a chemical dosing system has failed.
And I mean, in our world, when dosing fails, it's not just a nuisance where you just go reset a breaker.
Right.
An unmetered slug of acid or, sodium hypochlorite dumping into a line
Right.
that is a serious code red safety event.
It really is. I mean, it's the absolute definition of a high-stakes environment.
100%. You aren't just moving water from point A to point B. You're actively managing a volatile chemical reaction on a massive industrial scale. If you get a low wrong, or if a material degrades, your margin for error is razor thin. Before you know it, you're looking at severe equipment damage or a massive environmental compliance fine.
So today, we are cutting straight through the glossy marketing brochures. We're getting away from the sales pitches and getting down to the absolute hard numbers of fluid handling.
Which is so necessary.
Yeah. And this deep dive is pulling directly from the technical article sitting in the knowledge base on the DWT website. Our mission today is to build a flawless dosing system from the ground up, specifically for you, the engineer on the floor.
No fluff, just the engineering reality.
Exactly.
We're going to look at how you actually pick the fundamental pump technology, how you calculate the exact size using the critical 20 to 80% rule.
Which people mess up all the time.
Oh, constantly. And we'll cover how you avoid a very expensive chemical compatibility trap. And finally, how you prove the whole installation with a 5-minute test before you ever open the main process valves.
Let's start with the heart of the system then. Before you even look at flow rates or chemical resistance charts, you have to select the mechanical principle that's going to physically move your liquid.
Right, the actual mechanism.
Yeah. And looking at the DWT knowledge base, the baseline, the absolute workhorse for standard small system dosing is the solenoid diaphragm pump.
Yeah, if you're doing general dosing, up to about 20 liters per hour at pressures up to maybe 16 bar, this is your go-to.
Okay.
The mechanics are beautifully simple. You have an electromagnet that pulses a flexible diaphragm. When the magnet fires, it pulls the diaphragm back.
Creating a vacuum. Right.
Exactly. A tiny vacuum that pulls chemical up from the tank through a bottom check valve. And then when it releases, a spring pushes it forward, forcing the liquid out the top.
So every single stroke displaces a fixed calibrated micro volume.
Spot on. You set your dose rate by just adjusting the stroke frequency on the controller.
So basically no motor, very few moving parts. It's compact, economical, and extremely precise at those low flows.
It is.
But here's where it gets really interesting to me. The delivery is inherently pulsed. Like it's a sharp squirt, squirt, squirt.
Yeah, it's not a smooth, continuous stream at all.
Right. I'd imagine that introduces some chaos into the pipeline.
Oh, that pulse matters immensely. It dictates how the chemical mixes, and it really affects your downstream analytical instruments.
Because of the concentration spikes.
Exactly. If you have a chlorine probe just a few meters past the injection point, it might misinterpret a concentrated pulse as a massive, dangerous spike.
And then your controllers panic.
100%.
Hmm.
Also, once you need to push past that 20 liter per hour mark, you're stepping totally outside the comfort zone of solenoid tech.
Which naturally brings us to the big sibling, the motor-driven diaphragm pump.
Yep, the exact same diaphragm and check valve principle, but with a heavy-duty electric motor and a mechanical cam.
So this is the step up for like continuous 24/7 industrial duty at a major plant.
Municipal works, big sites, you're looking at flows reaching into the hundreds of liters per hour. The delivery is smoother, though still technically pulsating, and it has much better turn-down behavior.
So if you're dosing antiscalant on a massive reverse osmosis train, this is your standard.
Definitely.
And the cost is what you'd expect. It's bigger, requires more infrastructure, and it's substantially dearer.
But you pay that premium because you need that robust duty cycle that won't just burn out on you.
Right. Now, those two technologies make total logical sense to me. But the third one on our list, I really have to push back on this a bit.
The peristaltic pump.
Yes, the peristaltic. People either love them or hate them.
Mostly hate them until they need them.
Okay, so the mechanism is basically a set of rollers physically squeezing a flexible tube, right?
Good.
Pushing the liquid along like toothpaste.
Exactly. Nothing touches the chemical except the inside bore of that tube.
I get that it's great for very low flows or viscous liquids, but why on earth would a smart engineer deliberately choose a pump where the core component is a scheduled consumable?
I know, it sounds crazy.
It's literally designed to actively wear out from friction, and the pressure rating is tiny, like a few bar at most. Why buy a pump that destroys its own parts?
It sounds totally counterintuitive. But to understand why it's an absolute lifesaver, you have to understand what we call the hypochlorite gassing problem.
Okay, what happens with hypochlorite?
So sodium hypochlorite, standard industrial bleach, is notoriously unstable. As it sits in the day tank, especially as it gets warm in a South African plant room,
Oh yeah, midsummer.
right, it naturally degrades and releases oxygen gas bubbles.
Okay.
Now, imagine your standard diaphragm pump. It relies on a basic hydraulic rule.
Yeah.
Liquid is incompressible. The diaphragm pushes, the liquid has nowhere to go, so it lifts the check valve ball and squirts out.
Right, it forces the mechanical gate open.
But what happens when a gas bubble from that degrading hypochlorite gets sucked into the pump head?
Oh, gas is compressible.
Exactly. So the diaphragm pushes forward, but instead of lifting that heavy little ball, the energy is entirely absorbed by squishing the gas bubble.
And then it pulls back and the bubble just expands again.
Yes. The pump is running, clicking away, lights are on, but nothing is moving. It has silently lost prime. It's vapor locked.
Wow. It's exactly like trying to push a syringe full of water, but there's a tiny balloon trapped inside.
That's a great way to picture it.
The pump does all the work, the controller thinks everything is fine, but the chemical is just sitting there.
Meanwhile, your unchlorinated water is rushing past the injection point. You're risking severe biofouling downstream.
That is plant manager's nightmare.
It is. And this is exactly where the peristaltic pump shines. There are no check valves to jam or vapor lock.
Because the rollers just pinch the tube and physically shove everything forward.
Right. Liquid, gas bubbles, whatever. It just pushes the gas bubble straight through into the process. It self-primes incredibly reliably.
So if the complaint is the pump loses prime every afternoon, the fix is a peristaltic pump.
Or a highly specialized degassing head.
Yeah.
But the fix is never buying a bigger standard diaphragm pump.
Okay, distilling this for our South African technician. Solenoids for standard small stuff, motor-driven for big continuous duties, and peristaltic for gassing chemicals like hypochlorite.
That gives you a really solid mechanical foundation. But selecting the pump is only the first step. Now you have to size it.
Which brings us to the maths and the infamous 20 to 80% rule.
Oh, this is where people get into trouble.
Yeah, the DWT knowledge base points out that human intuition completely betrays buyers here. People buy oversized equipment thinking bigger is safer, or they want room to grow.
But in microdosing, bigger means you lose all your accuracy.
Let's walk through the arithmetic.
It's straightforward, but it has to be precise. Pump rate in liters per hour equals the main water flow in cubic meters per hour, multiplied by the required dose in milligrams per liter, divided by the chemical concentration in grams per liter.
Okay, let's ground this with the anti-scaling example from the sources. We have an RO plant. The feed water flow is 20 cubes an hour. We need to dose antiscalant at 3 milligrams per liter. And our neat chemical arrives in a drum at roughly 1,050 grams per liter.
Right, so running those numbers, 20 times 3 is 60. Divide that 60 by 1,050. That gives a required pump rate of exactly 0.06 liters per hour.
0.06 liters per hour. I mean, that is a startlingly small number.
It really is.
We're basically talking about a teardrop every few seconds, which brings up a massive issue on the plant floor.
The standard pump sizes.
Yeah. The smallest standard industrial pumps are usually around 5 liters per hour.
Yeah.
If we need 0.06 on a 5-liter pump, that's 1.2% of its maximum capacity.
Which completely shatters the 20 to 80% rule.
Yeah, why is that rule so non-negotiable? What physically happens if we try to run it at, say, 5% capacity?
Well, below about 10% capacity, the stroke-to-stroke repeatability is just destroyed.
Because the volume is so small.
Exactly. At 1.2%, the physical amount of liquid moved is microscopic. Any tiny imperfection, a soft microbubble, a worn valve seat, a speck of dust, absorbs the entire stroke volume.
So the stroke happens, but the liquid just slips back.
Yeah. Your accuracy quietly evaporates, and you're chronically underdosing without triggering an alarm.
And on the other end,
Above 80%.
above 80, you have absolutely no operational headroom. If the water quality drops and you need a higher dose, your pump is already maxed out at 100% speed. It physically cannot catch up.
Okay, so if I strictly need 0.06 liters per hour and my pump is 5 liters per hour,
Yeah.
Do I need to hunt down some incredibly expensive microscopic laboratory pump?
No, not at all. You don't change the hardware. The secret and the cheapest fix on any site is dilution.
Ah,
You change the fluid to match the machine. If we take that concentrated antiscalant and dilute it 10 to 1 with water in a day tank, our required duty jumps from 0.06 to zero point 0.6 liters per hour.
which puts us at 12% of our 5-liter pump, getting closer.
Right, so we dilute it further. A 4 to 1 dilution puts us safely right in the mid-range of that standard pump. Brilliant accuracy, no exotic equipment.
But there are strict rules for dilution, right? Very strict. You must use good quality water, ideally softened or RO water. If you use raw water, the calcium will instantly react with the chemicals
That makes sense.
and only mix what the plant will use in a few days. Dilute hypochlorite decays rapidly, and some polymers will hydrolyze and become useless.
And please, label the tank.
Yes, with a permanent marker detailing the exact dilution ratio.
Because the next technician on shift needs to do simple arithmetic, not archaeological forensics, to figure out what's in the tank.
Exactly.
Now, flow rate is only one axis. The second axis is pressure, and the sources point out a trap that catches buyers. Sizing the pressure based solely on the gauge right there in the pump room.
Oh, that is a classic expensive error.
Yeah.
You have to size the pump to inject against the real dynamic pressure at the actual injection point.
So if it's 50 meters downstream or up a 3-story pipe rack,
You have to add that static head pressure to your calculation, plus the tension of the spring inside the injection valve itself.
what happens if you undersize it?
The pump will just sit there clicking away. The controller says dosing, but the check valves will never open against that higher line pressure. It wears itself out without dosing a single drop.
Wow. Okay, so we have the mechanism, we diluted to hit the sweet spot, we calculated the true pressure. What if the main water flow isn't constant? Like a municipal line where flow spikes in the morning and drops at 2 a.m.?
Manual constant rate dosing would be a disaster there.
Yeah.
It would ruin the process. If water flow fluctuates, you must specify flow proportional dosing. You take a digital signal from a pulse water meter or a 4 to 20 milliamp signal and feed that directly into the pump.
So the pump automatically speeds up during the morning rush and slows down at night.
Precisely. It maintains a perfectly flat milligram per liter concentration. And specify that at order time because retrofitting a manual pump later is a messy compromise.
Good tip. Okay, our pump is perfectly sized, mathematically sound. But all of that means nothing if the pump starts melting from the inside out.
The wetted path.
Yes. Because if materials inside react with the chemical, the system tears itself apart.
Chemical compatibility is a chain, and the weakest link decides when it breaks. You can have a heavy-duty PVDF head, but if you have the wrong, tiny 2-rand O-ring inside it,
Catastrophic failure.
exactly, it fails just as badly as if the whole head melted.
Luckily, the standard setups are robust. You usually get PVDF heads and PTFE-faced diaphragms.
Teflon, basically.
Right. And those plastics have molecular bonds that are so tight, aggressive acids just bounce off.
Ceramic valve balls, too, they're basically chemically inert. But the real battleground where managers lose serious money is the elastomers.
The rubbery seals.
Yes. In water treatment, it's a heavyweight title fight between two materials, EPDM versus FKM. FKM is often known industrially as Viton.
And the DWT articles are incredibly strict here. They are not interchangeable.
Not even slightly. They split the chemical world right down the middle. EPDM is your go-to for oxidants and alkalis.
Like sodium hypochlorite and caustic soda.
Exactly. Its weakness. It falls apart instantly in oils, hydrocarbons, and concentrated mineral acids.
Yeah, FKM.
The exact opposite. It's the undisputed champion for highly concentrated acids, sulfuric, hydrochloric, and hydrocarbons. But its fatal weakness, hypochlorite.
This brings up a great South African analogy.
Oh, let's hear it.
Using FKM for everything just because it has a premium reputation is exactly like putting 50,000 Rand, low-profile, sticky track tires on a 4x4 backy that you're taking deep into the bush.
That is a perfect analogy.
Right. People see the price tag, they hear Viton, they assume it means the absolute best. But in the wrong environment, it fails instantly.
And that leads directly into what we call the hypochlorite trap. Because FKM has that premium reputation, buyers specify it by default.
Yeah.
The expensive pump arrives, gets installed on a hypochlorite line, and the bleach brutally attacks that premium seal. Over weeks or months, those seals harden, crack, and start to weep chemical.
And then there are mystery puddles of bleach on the floor, alarms going off, and the engineer furiously blames the pump manufacturer.
When the fault was entirely their elastomer choice on the purchase order.
Incredible.
The rule is blunt. Never use FKM on hypochlorite. Hypochlorite gets EPDM, period. If you have a standby pump alternating between acid and hypochlorite, you don't find a magical compromise. You buy two pumps.
That is a critical safety point. And speaking of safety, the sources have an urgent note on concentrated sulfuric acid.
Oh, absolutely. Diluting it is violently exothermic.
It generates massive amounts of heat. The rule is always add acid into a larger body of water, never pour water into acid.
Never. And above 90% concentration, sulfuric acid's compatibility profile shifts entirely.
Right. Materials that handled 50% acid perfectly will suddenly dissolve in 95% acid.
You cannot guess here. 2 minutes with a manufacturer's chart at specification time saves you from a catastrophic chemical spill.
Okay, the chemicals survived the pump, the elastomers are holding up, but we still have to get it into the process water.
The last inch.
Yes. The sources say this is where the most dangerous commissioning faults occur, the unvalved siphoning nightmare.
We have to remember, a metering pump only meters. It displaces liquid. It does not regulate flow.
Okay.
If the path from your day tank to your line creates a pressure gradient where the liquid wants to flow on its own, it absolutely will.
So if your tank is on a mezzanine higher than your injection point on the floor,
Gravity pulls it down. Or if the main line is under a strong vacuum, if you just run a tube directly into that pipe, the chemical gets sucked completely on its own, even if the dosing pump is powered off.
and if that siphon empties a 1,000-liter tank of acid into your process overnight, you've destroyed equipment and caused a severe safety event.
Exactly.
Mechanically, how do we stop gravity and vacuum from hijacking the system?
The fix is usually in the box with the pump. The back pressure valve or injection valve. It's a spring-loaded check valve.
So the spring imposes a deliberate opening pressure.
Right, one that gravity or mild vacuum can't overcome, but the pump can push past.
But the critical detail is where you install it. If you put it right at the pump outlet, the entire 50-meter length of delivery tubing is completely open to siphon forward.
Exactly. It belongs exclusively at the far end, right at the injection point.
And building that injection point is an art. You shouldn't just tap a hole in the side of the pipe and let the chemical dribble down the wall.
The sources are specific on that. Wall-injected chemical creates a highly corrosive streak. You can actually spot bad designs by looking for the discolored track of corrosion downstream.
That's why you always use an injection quill, a rigid probe that injects midstream into the turbulence.
Yes, and give it physical distance to mix. If you inject chlorine and put the sensor 10 centimeters downstream, the sensor just reads chaotic noise.
The control loop will go crazy, chasing phantom readings.
You need a straight run of pipe for it to homogenize.
Yeah.
And we have to talk about hard bore water here in South Africa.
No, the calcium.
Yeah, injecting alkaline hypochlorite into hard water causes calcium to precipitate. Over time, it grows a literal rock-hard calcium stalactite right at the tip of the quill.
So it's not if it blocks up, but when.
It's a constant maintenance item. You must install heavy-duty isolation valves on either side of the quill.
So you can just isolate it, pull it out, dip it in mild acid, and put it back. 10 minutes.
Without those valves, you're draining the entire main process line just to clean a tiny piece of plastic. Yeah. Massive waste of time.
Okay, we have the right pump, size, elastomers, injection quill.
Right.
The system is built. And now we arrive at my favorite part of the DWT documents, the 5-minute commissioning test.
Oh, it's brilliant.
I marvel at the irony. We spent thousands of rands, did intense maths, agonized over rubber seals, and the ultimate test to prove the system works safely is what happens when you turn it off.
It is deeply ironic.
Yeah.
But it's the ground-level truth. You prove the installation, not just the pump.
Right.
Test 1. Turn the pump O-off-F. Fill the clear calibration cylinder on the suction side, open the valves, and just watch it.
And if the liquid level drops while the pump is off, you have a siphon fault.
You fail immediately. Gravity is pulling it. You need to fix your back pressure valve.
And if it holds steady, test 2 is proving accuracy. You turn the pump on in and use a stopwatch to time the drawdown from that cylinder.
Exactly. You confirm that the volume drawn over 60 seconds matches your calculated rate of 0.6 liters per hour.
Those 2 simple checks catch nearly every fault long before the process goes live.
Yep. Switched off to prove safety, switched on to prove accuracy.
That is practical engineering. Okay, bringing it all together. A dosing system isn't just a pump you bolt to a wall. It is a holistic ecosystem from the day tank right through to the spring in the back pressure valve.
And remember, every single calculation and chart we cover today lives as a written technical article in the knowledge base on the DWT website.
Yes, waiting for you to use it on your next project.
When you understand the why behind the equipment,
Hmm,
Sizing stops being a guessing game and becomes an exact science.
100%. But I want to leave you, our listener, with a final puzzle to chew on.
Oh, okay.
We've spent this entire deep dive ensuring the mechanical pump delivers exactly the right dose. We've conquered the physics and chemistry. But what happens to your perfectly calibrated mechanical system when your downstream analytical sensors start lying to it?
Because they're covered in biological slime or scale.
Exactly. The digital probes telling the pump to speed up or slow down. How do you ensure your absolute mechanical truth isn't hijacked by a digital lie?
That's a scary thought.
Think about that next time you look at a perfectly green screen on a control panel. Thank you so much for joining us on this deep dive, and please double check your elastomer compatibility charts before you place your next order.